How do we know no isomorphism? Is it like 3 squiggly lines?
Why don't you fix the size of it?
Wow. Cannot find it, but we're going to say for now, if they're isomorphic, we're going to say G1, squiggly line, G2. That looks about right. Or is it squiggly, squiggly? Okay. Equal G2. It's just symbolic. If there's isomorphism. If you want isomorphic G2.
Yeah,
okay.
I know. Okay,
so an example.
Yeah,
it is an isomorphism.
Get rid of this.
Specifically, the mapping
area here. So
5
centers everything attached to that line.
equals. Okay.
Right.
1 is set to 0. So 0.
You got rid of this. Otherwise, you
If
have to keep that.
x equals 1.
I have to do this every time I move something.
2.
Reattach it.
Okay. If x equals negative 1.
The other is remove everything on
1.
first.
If x equals I.
And
And
once
3.
you remove everything,
If x equals negative
what I
I.
like to do is just get rid of this line up here.
Yeah. Is a bijection is a isomorphism. Because it's a bijection and a homomorphism from the set 1, negative 1, I, comma, negative I, the group formed by this set and the multiplication is isomorphism in this group to, or between, let's say from, I mean it is between, but I want to do that, to the Z4 under addition mod 4. So that's one example. We did one example together. Another example, let's look at one from last week. So last week we covered C. So last week we had the function 5x equals e to the x, right? And we said it's a bijection from R to R positive. However, we also have an isomorphism. So let's look at the group from R under addition. And we're going to look at the group R under multiplication, R positive under multiplication. So 5, or I think it was a mapping from this set. This set. So let's say, so it takes R. So we're going to check this. So we know it's bijection from last week. Now we're going to check these all measures
inside there.
So 5x1 plus x2 plus addition equals, by definition here, e to the x plus y by addition, by multiplication properties of x is e to x times e to y. This guy is equal to phi x times phi y. So by definition, this is homomorphism. And because we proved it's bijection, it is an isomorphism. Okay, so I gave you 2 examples of isomorphisms. For homework, you'll be doing a lot more examples. You have to come up with examples of your own. So, just some very good properties. So, inverses are preserved under isomorphisms. So, okay. So, given these two groups, G1, comma E star 1, and let E1 be the identity.
I need to be able to move something without it.
E1. And let's consider group 2, G2, comma star 2, and consider the identity E2, G2, comma star 2. So, okay. So 5 of E1. I'm going to prove this. In 5 maps E1 to the identity G2. And here's the proof. Very simple. These are the type of proofs you should know straight off the top of your head. It takes 10 seconds. So apply E1 equals well, identity times identity. This really just A1 equals identity times identity. So this equals to phi of E1 times E1, right? But this guy, in multiplication E1, this guy is equal to phi of E1 times 2 by E2. And that is by the property of homomorphisms. So look, we have phi E1 on both sides. And we're working in stuff in G2 right now. So this is so we take, by definition of groups, we have inverse. We take inverse of both sides. This tells us E2 equals phi E2. Done. First theorem. Second theorem. Theorem. Phi of x inverse equals phi x inverted. So it maps the inverse of x to inverse of phi x. So inverse is mapped to inverses.
It's still
Very simple.
that's
Phi of x inverse times x equals, by homomorphism property, phi of x inverse times phi of x. We also know this guy
take everything
is equal to phi of b.
reconstruct it.
What is phi 1 equal to? We just proved it was equal to phi b2. So let's just get rid of the intermediary steps. So we have phi x inverse times phi x. Sorry, this is equals phi e2. Or it's equal to e2, I'm sorry. It's supposed to be, it was phi e1, that's actually equal to e2, because what we just proved. So this guy should really take the inverse of both sides of phi x on the right. That says phi x
Probably faster.
equals the inverse on the right. Phi, I'll just write it out. Phi x times phi x inverse equals e2 times phi x inverse. This guy is equivalent to phi x inverted inside equals phi x inverse. So we're done. Okay. So you can see if we have inverses preserved and multiplication preserved and also identity preserved. This gives me an idea that maybe the subgroups are preserved. And in fact, it is. And I want you to prove that, reprove that in the reading. Good. There's many properties isomorphisms, very important. It is a way to relate different groups, and also not only relate groups, but relate different things in real world with mathematical groups. It's nice, I like it. Okay, anyways, I'm heading to another country in a few days. Maybe the next lecture will be delayed, I do not know. But it's been nice teaching you, and good job again, James Benedict. Math Ninja out.